So welcome to Quarks at 50. I'm Peter Fisher, the physics department head, and I'd like to thank everyone for coming. I'd like to particularly thank the organizing committee led by Herr Dr. Professor Christoph Marie Ernst Paus. I was CC'd on every email that committee exchanged, so I know what went into organizing this meeting. I'd also like to thank my staff, Christina Andujar and Ryan Higgins for their job, and Nicole Loria and the LNS staff for the work they did. And I'd like to thank all the speakers, some of which had to travel great distances to come here. Just by way of introduction, I'd like to go back to 50 years to what I was doing in 1969, about 9 o'clock on a weekday morning, eating Lucky Charms or something. And my dad read to me from the newspaper about this discovery that had been made at the linear accelerator at Stanford. And I grew up in Marin County, which is north of San Francisco, and Stanford is somewhat south of San Francisco. And in my parents' snobbish view, the world ended at San Francisco International Airport, and anything further down was referred to as down the peninsula, as in there's nothing there, there's no reason to go there, maps end. And so we were actually quite fascinated that something had happened down the peninsula, and I was very intrigued that there was an accelerator that was 2 miles long, and somewhat intrigued that there was actually something inside of the proton, because as a child, I had studied nuclear physics because the year before, we had gone to Disneyland and I had ridden on Monsanto's trip to inner space, where you are shrunk down eventually to atomic size. And I remember this pulsing red proton that was the nucleus, and the voice saying, "Dare I probe its interior? No, far too dangerous." So I was very excited that somebody actually had. 16 years later, I was sitting in David Hitland's Introduction to Nuclear and Particle Physics class, taught from Halsen and Martin, which was the standard text of the day. And probably the 7th or 8th week, we got to deep inelastic scattering, and chapter 7. And so there was a diagram of the experiment, which consisted of 2 lines, 2 boxes, and a semicircle. So there was a line labeled 22 GeV electron beam. There was a box labeled proton target. There was a dotted line at some angle labeled scattered beam. And then there was another box labeled electron detector, and a semicircle indicating that you could move the electron detector back and forth and measure some angular distribution. So we went on to apply relativistic Rutherford scattering to constituents of a proton, and found out that, in fact, the data did indicate that there were hard constituents to a proton. We did problems 2, 4, 6, and 8, where we learned what X, Y, nu were, and then something about structure functions, and we're done. Protons. It was really easy. And quarks in a proton. And I remember walking back to my lab. I was doing my thesis on neutrinoless double beta decay, and that was really complicated. There were these matrix elements, and Majorana neutrinos are really tricky, and the apparatus was more than 2 lines, 2 boxes, and a semicircle. And thinking like, wow, those guys really had it great, because it was all just so simple. You just built this thing, and quarks came out. So the message to the students in the audience is, it's hard for every generation. Experiments always are operating at the very limits of what you can do. And these days, for our students and young faculty, the limitations are, root, GEONT 4, and FPGAs. And the barriers are always, some weird compilation error, or the FPGA not working, or some problem with root. So today we're going to be privileged to hear what 50 years ago scientists face in discovering what was actually inside the proton. And I will now turn the session over to my colleague and mentor, Jerry Friedman, to start things off. So thank you very much for coming again.
The discovery of the internal structure of the proton 50 years ago, it brought back memories when I was a student at the University of Chicago. I remember going to classes about pion scattering and strong interactions, and the statement was made by many people at that time, and this was Enrico Fermi's physics department, so there were really very, very high-level people there. And the statement was made that the problem of strong interactions would not be solved for at least 100 years. It was so complicated. It was a strong interaction. Field theory didn't work because perturbation theory didn't work. And so therefore, what do you do? And it is very satisfying that in my lifetime, I was able to see the discovery of quarks and discovery of quarks leading to QCD, which is the theory of the strong interaction. So it's a wonderful celebration to be here today. I see many friends out there whom I haven't seen for a long time, and it's very satisfying. It is only very sad that Henry Kendall and Dick Taylor are not here with us to share the joy of this celebration. They were wonderful colleagues and friends, and we all miss them very much. So today we'll hear a series of talks, both theoretical and experimental. Not only will the origin of the quark theory be discussed by George Zweig, but there'll be presentations of the experiments and the various tests that the experiments had to go through to confirm quarks. So our first speaker today, and we're very fortunate to have him, is George Zweig, one of the fathers of the quark model. Soon after George finished his PhD with Dick Feynman at Caltech, he developed the quark model. But I really do feel that George never has gotten the credit for this outstanding work that he deserved. And I hope that this will be changed in the future. At any rate, he will tell us about what motivated him to develop this model. But let me say a few things about George. George has done research both at Los Alamos and MIT. He's also made very important contributions to neurobiology, so he's really covered quite a wide range of science. He won the Saccharide Prize in 2015, and he's also was awarded other honors. And it's a great pleasure to call George to the podium to give his talk.
So the first inkling that I had that hadrons had constituents came from the observation that a particle, the phi particle, didn't go into rho pi. The experiment was the one you see, k minus plus p goes to lambda plus k bar. And the k bar was seen to resonate into the phi as you see here, but this decay didn't happen. The authors of the paper say the observed rate for phi goes to rho plus pi is lower than predicted values by 1 order of magnitude. However, the above estimates are uncertain, but by at least this amount, so that this discrepancy need not be disconcerting. Well, I was very disconcerted because the sum of the masses of the k and k bar were almost the mass of the phi, and that wasn't true of the rho and the pi. And that meant that phase space was really not available. Not much of phase space was available here for the decay, but it was for the rho plus pi. So I estimated what the branching ratio was for kk bar and rho pi, and I found out that the rho pi decay was suppressed by a factor of 140, not 1 order of magnitude, but more than 2 orders of magnitude. And so I went in to see Feynman, who was my thesis advisor at that time. I was very excited, and I showed him the calculation and the data, and he said the experiment's wrong. And the reason the experiment was wrong, according to his view, was that unitarity mixes all particles of the same quantum number. And so it's impossible to single out the rho pi and not have phi decay into it. And then he went into a tirade and told me about how when he invented the V minus A theory for beta decay, that all the experiments were against him. And that, in fact, was true. However, I had learned from Feynman that in hadronic physics, everything that possibly can happen does, and with the maximum strength allowed by unitarity. And the only way you can get some suppression is through a symmetry. And there was no symmetry present. So there must be somehow a dynamical mechanism. I went off to CERN and worked in the country, hardly ever went into the office, and went back to my youth and started to think in terms of Tinker Toys. I know this seems like a very strange thing, but I had a very unusual education as a small child, which I don't have time to go into now. But in any case, here are the various constituents, and here are the forces that lock them together. So I thought that perhaps the hadrons had constituents, the constituents that you see up here, and I called them aces. It's a funny name, but there's a reason for it. Actually, there are two reasons for it. One was that ace comes from the Latin word as, which means the unit. And so these were the units of hadronic matter. The other reason was that aces appear in a deck of cards, and there are 4 aces in a deck of cards. I only needed 3 at the time, but I thought that these were point particles, just like the leptons. And so there should be a correspondence between the fundamental units of the strong interactions and those of the weak interactions. And in fact, later on, a 4th one was found, in fact, 2 more. So when I looked at the phi and its partners that had the same spin parity, I saw this array of masses where these two have the same mass, and this gets bumped up, and this gets bumped up. So tentatively, I said that these are made out of what I call deuces. So the rho and the pi, the rho and the omega, since they had approximately the same mass, at some level could be considered to have the same representation. The K star, which is heavier, would be like one of these, but you get this replaced with something which is heavier, and the phi actually with 2 replacements and would be heavier yet. So then I had a rule for hadron masses. I said that the masses were sum of the constituent masses plus all the energies of interaction. So that accounted for why I used the same deuces here for the rho and the omega. But it also meant that if these energies of interaction are all the same, the mass, twice the mass of the K star minus the mass of the rho should be the mass of the phi. And in fact, it approximately was. Now, what about the couplings? Well, to get the couplings, what I thought was, these are all hadronic couplings, get in the case of mesons, the deuces that are involved, the 3 of them over here, and see if you can fit them together. If you can fit them together, the reaction goes. If you can't, the reaction doesn't go. And you see here, this and this can be matched together. This is an ace, this is an anti-ace. And you can move the K minus over here and get this to match and get this to match, and you get a closed structure. The rho and the pi don't have any of these boxes, any of these lambda zeros. And so the K doesn't occur. When I went in after CERN, when I got back to Caltech, I went in to talk to Murray and show him what I had done. And I went through some of what you're about to see. And when I was all done, he looks up from his desk and he says, "Oh," he says, "the concrete quark model, that's for blockheads." And that's where the name concrete quarks comes from. So although I call them aces here, later on I called them concrete quarks, whereas Murray's objects are just plain quarks. Now, you can also get a graphical representation like this for meson-baryon couplings. Here you see the representation that I have for a baryon. Here's another baryon, and you see I'm getting matches, and this would be one contributor to a coupling, for example, of lambda p and k minus. Now, other baryons, like those in the baryon decaplet, were represented by equilateral triangles because there was more symmetry there. But for the octet, which we're considering here, the triangle, in fact, is asymmetric, and we'll see what some of the consequences of that are later. But in any case, because of this asymmetry, it matters where the deuce couples to the two trays, either up here or over here, and that was responsible for F-type couplings and D-type couplings in meson-baryon scattering. Well, later on in the spring, and then in the summer, I decided to include spin explicitly and work with the symmetry group, the group of all permutations. And once again, I represented baryons with these three objects, what I call trays, and the mesons as deuces. And the idea was that if all the ace masses were the same, and there was no force between the aces, no difference in the force between aces that depended on their spin, then there should be a higher symmetry that's present for the spectrum of mesons and baryons, and that the spectrum should form, the groupings should be according to the irreducible representations of S6, the symmetric or the permutation group of 6 objects. So if you look at the representations of S6, you see you have the 56-dimensional representation. But if you pay attention to spin-dependent forces, it breaks down into 2 representations of S3 or SU3, an 8 and a 10. The 8 has spin 1/2, and the 10 has spin 3/2, and that was exactly what one saw for the low-lying baryons. Now, if there was some symmetry present that's broken, there should be a mass relation between the members of the octet and the members of the decaplet. And you see that mass relation here. The mass splitting between the psi and the sigma should be equal to approximately the mass difference of the psi star and the sigma star in the decaplet. And in fact, they are. When you look at the mesons, you're working with the 35-dimensional representation of S6. And once again, with spin-dependent forces, you get an 8, and an 8, and also another 10. I grouped these together because they had the same spin parity so that they could mix with one another. And you get, once again, a broken symmetry relation, a relationship between the mass of the K and the pi, and the mass, the vector meson difference, the K star and the rho, and you get some incredible equality, which I just take to be accidental. The main point is that there's nothing that violates this idea. Well, what breaks the symmetric group S3 or SU3? The answer is given in the abstract of the first CERN report. It says the breaking of SU3 symmetry is assumed to be universal, being due to the mass difference among the aces. And you've already seen an example of that. If you say the mass of the lambda 0 is heavier than either the mass of the P0 or the N0, then you find this ordering of masses which is observed. Another example where you're looking at the mass difference between the P0 and the N0 comes when you assume that the N0 is heavier than the P0, and then you get the relation that the more negative a baryon is in a multiplet, the heavier it is, and that was true for all the known multiplets. Now there's a deeper idea that's involved here. The fact that the breaking of the symmetry is due to the mass differences and not to some kind of symmetry breaking term in an interaction was an indication that, in fact, there will be no SU3 symmetry breaking terms in a field theory with aces. SU3 symmetry is there not because it's actually a fundamental symmetry of nature which gets broken. It's there because aces have different masses. And I think this point was really not appreciated. Okay, so to give you an example of what these ideas are, I want to find the mass relations for the baryon octet when all the ace masses are different. But before I do that, I should have mentioned that there was a rule, Murray coined it, Zweig's rule, that allowed you to compute all the couplings between hadrons without paying any attention to SU3. And that idea, as I say, was called Zweig's rule. And the idea was the following. All you need is an expression for the wave functions. Once you have that, you form all the deuces and trays and you just put them down on a table. And you see all the ways in which you can assemble them. And then you count them, weighing them by the coefficients of the deuce or tray that's present in the wave function. And then you get your coupling. That's all you need. You just need the wave function, which you get from the symmetric group, and then all you have to do is put these tinkertoys together and see how many ways you can do it. Now, when it comes to masses, this is how you proceed. Here also, all you need is the wave function. So for example, for the Psi-0 octet, and this comes from my lectures in Erici in the summer of '64. This is called the Young tableau. And I said that the wave functions for all of the mesons and baryons, all the hadrons, is just given by some Young tableau, some way of representing an irreducible representation of the symmetric group. So the Psi-0, then, once you have the Young tableau, ends up telling you that the Psi-0 has two manifestations that occur with equal probability. This one and this one. Both of them have two lambda zeros, but in different order. And that different order is reflected in this asymmetric triangle that you saw before. So to get the masses, we assume that all forces between aces are just two-body forces. And when we do that, we have what you see over here. So this is from the second CERN report. This is the pictorial or tinkertoy representation of the baryon octet. Here's the proton, the neutron. Here's the Psi-0 that we just discussed. And it's a linear combination of two terms. And each of these terms has two lambda zeros, but they're located in different places, just like the order of the lambda zeros were different in the wave function that you saw. And then I just used the rule for the masses. The mass of the Psi-0 is the sum of the constituent masses. That's there. And then there's an energy of interaction. These lines represent the forces that are holding the aces together. And we just have to deal with two-body forces. So for example, we have a term here, and here this is position 1, 2, and 3 in the index, 1, 2, and 3. So this is a force between a lambda 0 and a lambda 0, and this guy is a spectator, so I don't put anything there. And then here I have a force between this guy and this guy, that's the lambda 0 and the p0, and this guy is a spectator. And then I weigh each of these terms, it's not written here, by the probability that each of these is actually acting. And then I do it for all of these cases. And then a remarkable thing happens. If you look at the mass difference between the Psi minus and the Psi-0, you see that it's the mass difference of two differences. This mass difference and this mass difference. Psi minus, Psi-0, and neutron and proton. In 1963, I got 6 for this mass splitting, and I'm sorry, 7 and 6 for this difference of mass splittings, and the error is 1.3 MeV. Today, when I look it up, I get this number and this number, which are very close, closer, in fact, than they're entitled to be given what the estimates of the errors are. So the errors have fallen by a factor of 6. So if you wish, this is a predictive statement. It says if you look more carefully and you wait in time, you actually will find a greater accuracy. Well, the rest of the story is complicated. It's complicated not conceptually, but there's just many, many things that one finds. There are relations between different decaplets, and I've just shown you some examples here, different, I should say, multiplets. There are particles that should exist, particles that shouldn't exist. There are excitations due to the fact that aces can rotate around one another. And when they rotate around one another, there are spin-orbit forces that split their masses, and that's observed. There are vibrational states. All this is described in more than 120 pages in both the Erici lectures and the second CERN report. I just want to call to your attention one thing in the second CERN report, which is relevant today. It has to do with where we should look for aces. It talks about various possibilities, what the mechanics are of aces inside of hadrons, and it ends up with the statement, consequently, high momentum transfer experiments may be necessary to detect aces. And in fact, that was true. I didn't, in any of these reports, say look at accelerators. And the reason was that I thought aces were tightly bound in some potential whose height I didn't know, and I didn't know how much energy was necessary to liberate them. People hadn't seen aces, that is, these anomalously fractionally charged particles at accelerators before. They could look more carefully, but the chances that they would be just at the right energy, I thought, was not large. And so I thought that one should look where theory says, that is inside protons and neutrons, and the only way you're going to do that is with high p-perfect scattering experiments. I do want to say that all this is not as simple as it looks. What I was working with in 1963, where really all of this work was done, except for some of the work in the Erici lectures, this data set lists 26 mesons, 26 here. We now know that 19 out of the 26 do not exist. If you look at these 19, 7 of them could not be made out of deuces, cannot be made out of quark-antiquark pairs or ace-anti-ace pairs. And so straightening all this out and reconciling it was a complicated issue that I don't have time to talk about. But the fact that I was trained as an experimental physicist was actually essential in trying to determine what I should believe and what I shouldn't. So let me summarize what was in 3 ACE papers, and this in the following slide. An S6 symmetry limit exists, and the wave functions are found from the irreducible representations of the S6 symmetric group. The couplings are found from Zweig's rule, that is, just trying to see how many ways you can assemble things and weigh them appropriately. The symmetry was obviously broken. The forces between aces was spin dependent, and so the S6 symmetry went down to an S3 symmetry. And when you let aces have different masses, they went from an S3 symmetry to an S2. This is where you distinguish the lambda 0, which is a lot heavier than the P0 and the N0. And if you distinguish the P0 and the N0, there is no symmetry. And it goes down to S1. A point that I want to emphasize is that dynamics suggests existence. What does it mean to say that you have aces and they orbit around each other and they have a spin-orbit coupling if they're not real particles? The third major, or second major, I think, understanding was that you should look for aces in high momentum transfer experiments. And this was also interesting. It was that the symmetries SU6 and SU3 are not fundamental. They're not going to be found in the theory for the hadronic physics when you finally write them down. They have to be outputs, not inputs, to field theory for ACEs, where you have different masses and spin-dependent forces. I also wanted to read from the conclusions of the second CERN report. It says here, there are, however, many unanswered questions. Are ACEs particles? If so, what are their interactions? Do ACEs bind to form only deuces and treys? What is the particle or particles that is responsible for binding the ACEs? And why does so simple a model yield such a good approximation to nature? And the report ends with a sentence, there is also the outside chance that the model is a closer approximation to nature than we may think, and that fractionally charged ACEs abound within us. And indeed they do. In retrospect, I have a comment for students. There aren't many students up here, but they may have the patience to do and the intellect to do the work. That is, I think what we should do is use QCD to compute all these many relations that were responsible for the origin of QCD. It's amazing you got a theory and you have no idea what it was or how to understand what people were looking at, which led you to invent the theory in the first place. It's a very unsatisfactory situation. If you do this and are successful, you'll test QCD and you'll provide insight into that theory. And finally, at least for me, ACEs were not invented, but discovered by looking at data, and their existence confirmed in 1969 in a high momentum transfer experiment. Thank you.
Thank you very much, George, for a very interesting talk. It gave you great insight about how you came up with this idea, which is a very detailed observation of phenomena, which is a very interesting way of doing it. We have time for 2 questions. Does anybody in the audience want to ask a question? Yes. I can bring the microphone.
Looking at the dates, and especially on your first CERN report, it seems that it predated Gell-Mann's work on quarks. He really got the idea from Robert Serber.
Pardon me?
And he got the idea from Robert Serber.
That's right.
And I think it was March of 1963.
That's a separate story. That's Murray's story, and I'm not dealing with that, but you're right.
My question is, why didn't you publish it more formally?
Pardon me?
Why didn't you publish the ACEs idea more formally than a CERN report?
I wasn't allowed to. I was a postdoc. Actually, I was still a graduate student when I was at CERN, technically a graduate student. And I had 2 fellowships, one from the National Academy of Sciences, the other from National Research Council, and then the Air Force Office of Scientific Research. And they gave me money, paid my salary, and paid for my overhead, and paid for publication charges. And when I submitted my paper to be sent to the physical review for publication, all papers before they were published from the theory group had to be approved by the Director General. And the Director General wouldn't allow me to publish in an American journal. I had to publish in a European journal. I also was going to give a talk on the subject. The title of the talk was Dealer's Choice, Aces Are Wild. And it was up there on the corkboard, and I saw Van Hove come out and take the announcement off, and he said, "You're not allowed to talk on this subject at CERN." The Erici lectures were published, but a year later, because it takes a while to get out. I couldn't get them typed. he had also instructed his secretary not to allow her to type any of my papers. But the secretary at the time, Madame Fabergé, she took pity on me because I didn't know how to type and didn't have a typewriter. And she actually typed up the Arachi lectures, but it couldn't get published because it needed the director's approval. And she also didn't want the director to know that she actually typed my paper. So
Director General, it was Van Hoven.
I'm sorry, I don't mean the director. He became the director general eventually. He was the head of the theory division at that time.
Another question here? Well, in this case, let's just thank George again for...
Thank you.
Our next speaker is Chris Llewellyn-Smith. Chris did extremely important work. He developed theoretical tests of the quark model, namely a number of sum rules, which played a very, very important role in the confirmation of the quark model. Chris got his PhD at Oxford in theoretical physics. He went on to a very, very distinguished career. In addition to this career, he had some extremely important administrative responsibilities. He served as Director General of CERN. He also served as Provost and President of University College London. Chris has received many honors, including medals from the Royal Society and the Institute of Physics. And it's really a great pleasure to have him, and I want to thank him for the long trip he took to get here. Let's welcome Chris Llewellyn-Smith.
Thanks very much, Jerry. Well, thank you very much. Actually, I'm delighted to be here, but I'm also sorry, because I'm here because James Buchanan, BJ, had not been well and couldn't get here. So I'm very, very sorry to hear that. And I'm also sorry because he was one of the heroes of the story I'm going to tell, and you ought to have heard the story from him, not from me. All I can say is that I think I'm going to be better at blowing BJ's trumpet than he would have been himself. And I think he'd rather dislike my talk because I'm going to do that. I was at SLAC for 2 of the glory years and spoke to BJ daily, so I know that of which I speak. Now, the name Gell-Mann is indelibly connected with quarks, but as we just heard, he got the idea from Serber. It's described in Serber's memoirs in great detail. And Murray, in fact, said that quarks were purely mathematical, and his attitude certainly intimidated us, and who took quarks seriously, and perhaps held back the development of the model. And the true hero you see here at a younger age of the concrete quark model, George Zweig. I think we should also mention Andre Paperman, who actually was the first person to submit a paper on quarks. But it was quoted once in the subsequent 40 years. It was in French, it had an obscure title, and I could say a lot more about it. But he was actually the first. He had a number of results, but nothing like as much as George. I'd also like to acknowledge my supervisor, Dick Dulles. Dick worked tirelessly to show that the many new particles that were being discovered almost daily in the 60s fitted into the model, and that was by no means obvious. Some of you will remember the time when a meson called the A2 was claimed with what seemed to be rather good statistical evidence was actually 2 states. If that had been correct, that one measurement alone would have been enough to destroy the quark model. So it all looks simple in hindsight, but at the time, every new discovery could have destroyed the thing. Now, I was following the sort of smart money and saying quarks must be wrong and trying to talk Dick Dulles out of it. He had me working on something else, until one day I found myself saying, the quark model's stupid, but it's a very good way to remember the data. And I thought, what a stupid remark. What more can you ask of a model? This was in 1966. So I became an early believer in quarks, and I owe my career to that, I think, because there were few of us. So despite its success, few took the quark model seriously. But that number increased slowly from late 1968, when the deep inelastic scattering experiments at SLAC pointed to point-like objects in the proton and neutron and gradually established their properties. So here is the large momentum transfer experiment. Electron plus proton goes to electron plus something. Hit it as hard as you can. Electrons down the 2-mile accelerator. Here's end station A and the spectrometer. You'll hear more about that later. The results surprised most people who thought that the cross-section would be rather small. And there is a direct historical analogy for that with Rutherford's surprise when he had Geiger and Marsden, his assistants, scatter alpha particles from a gold foil. And he thought that the nucleus had a sort of fuzzy object with the charge diffused, and they'd mostly go forward. And they told him we get backscatters. And here is what Rutherford said. He said, "It was quite the most incredible event ever happened to me. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." And he correctly interpreted this as saying that the nucleus actually is mostly empty space and the charge is just concentrated in the protons. And that's exactly the story of what happened at SLAC. Now, who was not surprised? I think among theorists, probably only BJ. The experimenters, they probably expected something like this. I don't know. We'll be hearing from their collaborators later. Now, I think it's important to remember the context in the 1960s. Field theory was thought to be irrelevant except for quantum electrodynamics. The leader, Murray Goldman was following this idea, although he was very careful to hedge his bets and choose the words that he'd have an escape route. But the leader of this movement was Geoffrey Chew, and here's a quote: "Conventional association of fields with strongly interacting particles is empty. Field theory, like an old soldier, is destined not to die, but just to fade away." That was the atmosphere in which we students were sort of brought up in the mid-60s. The first two major conferences that I went to were in 1969, and they show you the contrast. The first was the European Particle Physics Conference, not a global conference, just European, but about all particle physics, 610 participants. A month later, I was at the Liverpool conference, the Photon-Electron Conference. That wasn't regarded as interesting. The way ahead was with Padrons. World Conference, 240 participants. That's the first time I met BJ and also Pete Panofsky. Attention in electroproduction was focused on specific channels. EP goes to EP. EP goes to E plus an excitation of the proton, the delta. And those cross-sections fell off very rapidly with momentum, just showing the quarks like to break up. They don't like to stick together. They're fragile. EP to EP plus anything was generally considered uninteresting insofar as anybody thought about it. And it was thought that cross-section by most people would fall off, and there was relatively little data. Now, as the first of a number of speakers going to talk about these experiments, it's fallen on me, I hope I get somebody else to do it first, to talk about introduce the nomenclature. So here we have the electron scattering through a large angle with large momentum transfer. So there are three variables, E, E prime, and theta. But the physics depends on just two variables because it doesn't see the electron, it just sees the momentum transfer. So it's a function of the form momentum of the proton and the form momentum of the virtual photon. So we can make two Lorentz invariant variables, q dot p, nu it was called, and q squared. And we're going to use q squared and the dimensionless ratio, and I'll come to the interpretation of that later. Actually, in the early days, we used the inverse of that, omega, because we didn't have an interpretation. Now, so the whole of the physics lies in two structure functions which depend on q squared and x, two dimensionless structure functions. Why are there two? Well, we can think of this as a virtual photon scattering of the proton. It's a total cross-section for the virtual photon. And like a real photon, a virtual photon can be transversely polarized, or if you like, it can be right-handed or left-handed. But by parity conservation, the left-handed and right-handed cross-sections are equal. But a virtual photon can also be longitudinal, have no component of angular momentum along its direction of motion. So there is a scalar cross-section, sigma s. So that's why there are two two bits of physics here to measure. I'm also going to talk about neutrino scattering, which is completely analogous, except it's scattering a neutrino to a mu and the virtual photon is a virtual W. But in that case, since parity is not conserved, sigma L is not equal to sigma R, and there are three structure functions. Now, in 1966, BJ, using very tortuous methods, which we used, of looking at commutators of currents and the time derivatives of currents, taking the limiters of momentum 1 to infinity and so on, derived the following sum rule without, whoop, I've gone too far forward, backwards rather. This sum rule, without this term here, that's a QCD effect, for the scattering of two of the additional structure functions if you have a polarized target. Obviously, the polarized target, you can polarize it against or towards, and there are additional structure functions. And here it is. They're also functions of x and q squared, and they're equal to the GA over GV, the weak decay constants. And he derived this without this term here. We now know that these results are invalid in every order of perturbation theory. That was known quite quickly, actually. I'll come to that. And we now know, actually, however, the first term is correct in QCD with a correction of order alpha strong. BJ said, this, you read the paper, this is a worthless result, I think because he thought, we're never going to measure this, but it's been measured and this sum rule has been tested. But he then went on to say, I can use this to derive an inequality for the unpolarized cross-section, and what it says is inelastic scattering is going to be large, comparable to scattering off point-like charges. This was 1966, the first reference to this idea. He says in the paper, the same techniques tell you that the E plus E minus annihilation cross-section to hadrons will go like 1 on E squared. And the paper says the idea that total hadronic yield should be approximately the same as the muon yield is folklore. Bert Richter, private communication. And I asked BJ once, really? Bert said that to you? He said, I don't think so, but I wanted a reference. So the same paper also says that the same idea says the neutrino cross-section would rise linearly with energy. And there were some relatively low energy neutrino data from CERN at that data, and the cross-section was, with huge errors, going up very fast. And the experimenters went to John Bell and Tini Veltman, who were in the theory group, and said, what does this mean? And they said, oh, that's too complicated, the total cross-section. Think about producing the elastic scattering or producing the delta resonance or something like that. Now, in 1967, in his Verena lectures and the SLAC conference talk, BJ went a bit further. He observed that he looked at the Adler sum rule, which is the difference of neutrino scattering, the analogous structure functions of a neutrino and a neutron and a proton, and found the following, that it integrates to 1. This sum rule is exact, now well tested, and independent of q squared. And it's equivalent to saying that the limit of infinite energy, the differential cross-section, is just Fermi's constant squared over pi. And he said in his lectures and in his talk, this is highly suggestive of point-like behavior. The result will be true were the nucleon a point-like object, because the derivation is general. Therefore, but the difference between these cross-sections is a point-like cross-section, and it is big. So BJ knew this was going to happen. And then he pointed out that this is a measurement of the difference between the number of isospin up and isospin down objects in the nucleon, and describe what today we know as the parton model. So here is what BJ said in the SLAC conference. If the nucleon's built of point-like constituents, which can be seen if you really look at it instantaneously in time, if we go to very large energy and large q squared, we expect the scattering will be incoherent from these point-like constituents. If the constituents had isospin 1/2, the sum rule simply says is the number with isospin up minus the number down is 1. Then he says, this gives a very simple-minded picture, which may look better if you really look at it, say, in the center of mass of the lepton and the incoming photon. In this frame, the proton is contracted into a very thin pancake, and the lepton scatters essentially instantaneously in time in the high energy limit. Furthermore, the proper motion of any of the constituents inside the hadron is slowed down by time dilation. Provided one doesn't observe too carefully the final energy of the lepton to avoid trouble with the uncertainty principle, this process looks qualitatively like a good measurement of the instantaneous distribution of matter of charge within a nucleon. So you had the impulse approximation for scattering off constituents. That is the parton model. He didn't write down a formula for it, but that is the parton model. Now, what happened next, because Feynman then came in a little bit later, slide beyond next, and he coined the name. Well, actually what happened next is in the next year, by these very tortuous methods of calculating commutators, taking the infinite momentum limit, BJ derived scaling, that these structure functions would become functions of x only as q squared goes to infinity. These formal methods are not correct. They are wrong in every order of perturbation theory. We learned, you'll see in a minute, but they're now known to work to lowest order in QCD and then be corrected. And then BJ says, a more physical interpretation of what is going on is without question needed. So it's slightly odd that back here he had a physical interpretation but didn't say there was scaling. Here he had scaling, but said we needed a physical interpretation. And about 4 or 5 years ago, I was having lunch with BJ, and I asked him, how is this? And he said, you've got to remember, we were treading on thin ice. We weren't really sure about what we were doing. This is all highly speculative. And it's really important to remember that. We didn't know what we know now. With retrospect, and hindsight, it's weird that BJ didn't put these things together. But he didn't, because we were all uncertain. In August, Feynman became involved, the next slide, and in September, the first data were presented in Vienna by Pief. The cross-sections are large, decrease much more slowly with momentum transfer. Theoretical speculations are focused on the possibility that these data give evidence on point-like charged structures, the apparent success of the parameterization in the variable nu over q squared, the dimensionless variable, in addition to the large cross-section, is at least indicative that point-like interactions are becoming involved. Now, what about Feynman? So this is a quote from Marty's talk. I think it's going to be on one of your transparencies, but I ripped it off from you. So many of us didn't understand BJ's current algebra, and indeed, these were tortuous, complicated methods. Feynman visited SLAC. He was developing the parton model for hadron-hadron scattering. We showed him the early data, and he, after a night in a local dive, explained the data with his parton model. In the infinite momentum frame, the point-like partons are slowed, etc. That's exactly what BJ was saying. This is wonderful and understandable. What I don't know is, well, why was BJ's parton picture wasn't taken on board? I think because he didn't, he was then talking about scaling with these methods, and it was a year before he'd given the picture, and he didn't put them together, and he didn't do calculations with it, but he came damn close. It's not clear to me, I guess it was Dick who made the interpretation, which is simply, if you look at high enough energy, if the proton has 4 momentum p, and you forget the mass of everything, the parton can be said to have 4 momentum xp. It absorbs a photon of 4 momentum q. You have a parton of 4 momentum xq plus xp. You square the 4 momentum at 0, because we're neglecting the mass, and you find x. This famous scaling variable just describes the fraction of momentum in the proton, of course. Now, in 1969, Dick gave the first talk he ever gave about partons, but it doesn't mention deep inelastic scattering. In 1970, he did give a talk mentioning it. It's entirely focused on this talk on hadron scattering. The first explicit model was made by BJ and Manny Pascos, who quoted Feynman. And this period, Sid Drell got involved with his collaborators, and they took a cutoff field theory, they softened, they put a momentum cutoff on all the integrals to see, could you get a model which would apply to other processes? So proton-proton goes to very massive muon pair was one of them, the Drell-Yan process. And this was quite important because they mapped out the processes which we subsequently know can be applied for QCD, because QCD is a softened field theory. They didn't have QCD, they weren't looking at quarks, but they had already identified the sort of menu to which we could apply QCD. In this same year, Kirk Callan and David Gross derived some rules that related integrals over F2 and F1 to the time derivative of currents with them, the commutator of the time derivative of current with a current, again in this complicated business in the infinite momentum frame. And this, the time derivative, the Hamiltonian comes in here, so this brings in dynamics. And in those days, there were two models for currents. One was that we'd take quarks, and if you're a good Gell-Mann follower, then throw them away, abstract the behavior of currents. But there was also something called the algebra of fields, that you'd take the commutator of vector fields, which had the same quantum numbers. And there was a distinction, and it's easy to understand. They found in the quark model, sigma L for longitudinal cross scalar photons over sigma T was 0. And that's very easy to see. If we think of a spin, if you think of a virtual photon hitting a spin-and-a-half proton in the frame where the quark is just reversed, the helicity is conserved, so you've got spin coming in, spin going out. So it can only absorb a virtual photon that carries 1 unit of angular momentum. So sigma L over sigma T will be 0 in the quark model. On the other hand, here, sigma T will be 0 because these were effectively spin-0 constituents, so they couldn't absorb anything which had angular momentum. So this is a very clear distinction. It's violated by QCD because in QCD, this quark could radiate a hard gluon and it's going a bit sideways. So then this process becomes possible. But this is really important, waiting for the first measurements of sigma L over sigma T. In '69, it was discovered that in every order of perturbation theory, and Roman Chakif was one of the people who's in the audience today, this scaling is violated. In the same year, I got involved in this. David Gross was visiting CERN, and he gave a flamboyant seminar about this is the work that's going on around the world, and he described the parton model. Now, it happened I was working with John Bell on neutrino scattering off nuclei, nothing to do with deep and elastic, but I knew something about neutrinos. So I wanted to see, had I understood David's seminar? So I worked out the parton distributions and went to David's office and said, did I get it right? And David said, well, that's a good idea. No one has ever applied this to neutrinos, which seems incredible with hindsight. I think BJ was doing it, but he hadn't published anything. Then David said to me, you've made a mistake. You've got a third structure function. There are only two. So I pointed out to him, not the case with neutrinos. He's a smart guy, so he understood that. And then he said to me, look, you've only looked at the parton distributions. Why don't we look at these commutators and go to infinite momentum? And we found a sum rule. Now, this sum rule, again, is known to be the leading order in QCD. And the 2 was over on the right in those days. I've reshuffled it down here. We had a 6. And David said to me, we must have made a mistake. Sum rules give results like 1 or 2. They never give 6. So I thought, I will check my algebra with the parton model. And I did it that evening. And I came back the next day and said, we've discovered a way of measuring the difference between the number of baryons and antibaryons in the nucleon. We rather arrogantly knew about these logarithms and said, there's no reason to believe field theory is relevant. It's contradicted by experiment. That's because we knew that there was supposed to be scaling. And then in this sum was very well tested, and it's nowadays used as a way of measuring the strong coupling constant. The first data came in September of that year for sigma L over sigma T, so that was very exciting for those of us who believed in the quark model. Now, in 1970, there were many ideas on the market still. Just because we know the quark one was the right idea in hindsight, it didn't necessarily true at the time. And I wrote down all the sum rules that you could derive in the most general parton model, and which I then re-derived with all this formal mechanism. And here they are. And I was particularly pleased with this one because I thought this is going to be a way of comparing electrons and neutrinos, a way of testing the quarks and the charge. That comes from the non-integral charges. But then I realized that's the same as saying that the cross-section for absorbing an isoscalar photon divided by an isospin-1 photon is 1/9. That's known to work for real photons. It's explained by the vector dominance model, so maybe nothing to do with quarks. And this was the sort of confusion we were in. Of course, it works for this as well because they're made of quarks. But in the same paper, I pointed out, probably known to BJ, the integral of F2 was quite hard to understand because it measures the average x of the partons weighted by their squared charge. And despite the fact these things were less than 1, this integral, the data was 0.18, and it was very, very hard to get down to 0.18. And in that paper, I said we could reduce this by adding a background of neutral constituents which could be responsible for binding quarks. And I gave a talk about this and was immediately told that's not in the spirit of the quark model. You're not allowed to think about that sort of thing. But I thought about it anyway. At this time, I think we all knew that measuring the neutron cross-section as well as the proton, only this was known, this one wasn't, was going to be a very important discriminant between these models. In fact, it was pointed out some years earlier in a simpler model by Gottfried. Now, in 71, I put some things going on in the background here, like finding gauge theories were renormalizable. I turned that result into a sum rule for the amount of, this combination measures the amount of momentum carried by quarks. Or minus it. You take it away from 1, you've got the amount in the gluon, and that was the result. And in early 71, Murray Gell-Mann came to SLAC, and he gave a talk in which he said, I'm going to use the light cone algebra, which meant free field theory with no gluons. And that was sort of what I'd done the year before with the parton model. And I was a young postdoc, and huge, full auditorium, and very nervously put up my hand and said, you're going to get a result that's contradicted by the data. And Murray said, you must be Llewellyn Smith. So I was very pleased about that because I'd never met him. And then characteristically added, you spell your name wrongly. We'll talk afterwards. But his attitude was, we shouldn't give up only thinking about quarks with no force until we're absolutely forced, and there are still some errors here. In this year, Gribov and Lepatov summed up all those logarithms, and then this was reproduced by Chris Haslacher and Müller using something called the operator product expansion. And they reproduced that result. And that was the machinery that was later used to calculate scaling violations. So that was developed in this year. And in the same year, sigma antineutrino over sigma neutrino was found to be about 1/3 at CERN, which is what was expected for mostly quarks, not too many anti-quarks. Okay. Nearly there. So going forward, where I've gone backwards. Right. So in 1973, QCD came along, and asymptotic freedom was shown that if you added up all those logs, they ended up to 1 over a log. And the correction you got, it was all absorbed into a running strong coupling constant. So that was a great moment. And the physical picture of this, I think, developed by Ken Wilson, was that, and this gives scaling violations, as we'll see. Well, obviously, the alpha S is in the right-hand side of those formula, depends on Q squared. So the physical picture was, you've got your quark here, and you probe it with a certain Q squared, and you see a quark. But as you increase the Q squared, you get better resolution, and what you thought was a quark is a quark plus a gluon. You increase it further, it's a quark plus an anti-quark plus a gluon, etc., or quark anti-quark. So as you go higher and higher, what you thought, if you started with a quark carrying 0.6 of the momentum, you would see that actually, when you look deeper, the quark inside only carried 0.4. So there's a picture of the scaling violations, that the cross sections with Q squared, the structure functions at large Q squared would go down, as you resolve more and more things with less and less momentum, and at the bottom they'll go up. And I'm going to, on my second last slide, show you the data for that. The neutrino experiments at CERN came in at much higher energy. They supported the F3 summary and various things. But still then, it wasn't so obvious. There was something, whoop, what have I done here? How do I get out of that? Called the high Y anomaly in neutrino. I won't bore you if you weren't not old enough to remember, but there were contradictory results around. And the picture was, whoop. Can't remember what's on the next slide, or I could keep speaking. Here we go. Can you get it up to? That's it. Were the first calculations of QCD scaling violations, and then again, something came in which really shook the community. BJ had said that the E plus E minus cross-section divided by the muon cross-section should be a constant. But the first data from SLAC seemed to show it going up. So this was supposed to be a constant, seemed to go up, and that really shook people's confidence in the whole picture that we've been developed. Here is Bert Richter describing it in the London conference. I won't read through this, but he basically said, this seems to show that there's a direct, no photon annihilation, direct interaction, strong interactions of leptons with hadrons at high energy. Of course, the next year, charm was discovered, and we realized this was a constant, well, some sort of constant here. This is the charm threshold and settles down to a constant at a higher level up here. Now, this is my second last slide, Jerry, you'll be glad to hear. The first evidence of scaling violations, and here's some, came from SLAC. Here's some a lot later, up to colossal Q squared from the EP Collider, Hera, and Hamburg. And you see at large x, this is x equals 0.6, going down with Q squared as the quarks radiate away gluons. And then at the bottom, because the stuff they're radiated away, they don't vanish, they accumulate somewhere, the cross-sections go up. Charm was discovered, perturbative QCD, 3 jet events observed at DESI as expected. And in the subsequent 40 years, there's been overwhelming evidence for QCD, particularly exquisite results from LEP. It's now mainly as an interest as a background rather than the signal, this stuff. A lot of work on higher order corrections now used to constrain parton distributions and to measure alpha S. So a few personal remarks and conclusions. What we know is the standard model. Some of the roots go back before this period. Non-abelian gauge theories were invented in the 50s. The Goldstone boson was known, I've forgotten the date, Jeffrey Here's 1960 or something like that. The Higgs model was around in 1963. But when I became a graduate student in '64, essentially the nature of hadrons and the strong force were completely unknown, and we were told field theory is going to die. And there was nobody knew how to make a mathematically consistent theory of the weak forces. From 1964, from the discovery, not the invention, George, to the discovery of charm was a golden age that I was very lucky to be part of. The textbook history, Gell-Mann and Zweig invented quarks soon after SLAC showed they were real, has some pedagogical value, perhaps, but it wasn't like that at the time. There were forwards, backwards, dead ends, and so on. Few had the prescience of George and BJ, who were the experimentalists, the real heroes of the early history of the quark model. Thank you very much.
Thank you, Chris, for a very interesting journey through history and showing how circuitous some of the issues were. I just want to make one comment to give you an idea of how, in a certain sense, negatively community felt toward point-like structure. I was given the responsibility of presenting the first data at the Vienna conference. And of course, it was, we had, at that point, seen the possibility of point-like structure from the behavior, the Q-square behavior, and of course, the scaling at SLAC. And of course, the question came up when I presented the data, could I talk about the possibility of point-like structure? And a number of us wanted to, but it was considered such a bizarre point of view that we had a vote, and the ones who wanted to present point-like structure were voted down. So I never mentioned it. However, Peef, in his wisdom, when he gave the plenary talk, he did mention it and talked about the possibility of point-like structure being observed in these experiments. I was sitting in the audience, and it appeared there was barely any interest in that point of view. It was like dropping a stone in water and having some ripples go out, and it was gone. Nobody ever came up to ask any questions about it. It was such a bizarre point of view. It couldn't be true at that time. So that was the sort of the atmosphere of the time. So now we have time for a couple of questions. Any questions here after this very, very interesting historical journey? No questions? I guess you're
Here.
okay.
I can't hear you. Wait for the microphone. Probably won't be able to hear you then either, but let's try. You'll
I just
interpret.
Jerry, you say the atmosphere, maybe in the world as a whole, was that the point-like partons was strange. I was at SLAC at the time, and let me tell you, among the SLAC people, it was taken for granted that the results are point-like, but nobody. The opposite view would have been a surprise.
Well, the question is whether it was 1968, 69, or 70. But
I can tell you, I'm talking about exactly 69 August, because that's when I left SLAC.
No, by that time, actually, Dick Taylor.
That was true at SLAC.
Yeah.
But
Yes,
it
that's
wasn't
what I'm
true
saying.
in the rest of the world. I think that the SLAC-centric view of history is a little bit dangerous because it gives the impression SLAC switched on and everybody saw the light.
No,
but they did, as far as Sand Hill Road, but not across the bay necessarily.
In fact, in 1969, Dick Taylor, in the Liverpool conference, did talk about point-like structure. So at that point, the idea was it was possible. But there were 2 points, as Chris said. SLAC had a different point of view. The East Coast didn't know of anything about scaling, about point-like structure, and it was considered quite a bizarre point of view. Yes.
Chris,
Okay, George.
Chris, how did the discovery of the J psi meson change people's thinking?
Oh, because I think it changed it because this supposedly linearly rising E plus E minus cross section, I mean, that looked fatal. And I mean, of course, you get a really bizarre result. I put on the slide, I didn't read it out. Immediately, there are theorists generating papers explaining it. And they were all garbage. I mean, the fact was, it was just there was an additional quark.
No, but there's another issue that's involved, and that is that the J psi meson was extraordinarily narrow.
Yes.
Much narrower even than the phi. So when I heard that, I said, oh, that's the fourth quark. It's just deja vu all over again. Did other people think that?
Oh, that's correct. I mean, it was very narrow, and people were instantly saying, we can think of this in terms of QCD and the sort of language you've been discussing, that it's, it's a rearrangement, whatever
Well,
it
but
is.
how important was that in getting people to believe the idea that quarks were really inside of hadrons?
I can't really answer that because I believe that since 1966.
No, but what about the people around you? How did their thinking? Do people in the audience have a
I don't know.
comment?
Bob, you
Bob?
want to answer that?
Just a quick comment on that. I think that those of us who were at SLAC in the late 60s and early 70s were absolutely convinced that the SLAC discovery indicated that quarks were real constituents of protons and neutrons. The rest of the world, including physicists on the East Coast, maintained a kind of hedged bet. Physicists who were not involved in high-energy physics still were very skeptical, and the discovery of the J psi really nailed it for the whole physics world. People stopped asking questions about whether quarks were real in 1974.
Good, thank you.
First at CERN, and when I was in Russia before that, I gave a talk about the quark model. You'd spent the first 20 minutes fielding brickbats and explaining, sort of apologizing for what you were saying, almost.
I just visited Russia 4 years ago, and Bogoliubov immediately believed that the Quark model was right. And he told all of his people, these are real subjects and just think that way. The other person who immediately realized that the Quark model was right was the chemist Linus Pauling. So in 1964, he was going to put out a new edition of his book, General Chemistry. And in this book, or in this revision, which he sent me the proofs, he describes the Quark model. And he just said, did I get it right? And I just wrote back, yes, you did. So to some people, if they had enough distance from it.
I mean, I was in Russia 1967 months, 67 to 68. And I only spent a day at Dubna with the Bogoliubov group, and there was a good reception. But where I was in Fian, I don't know how your Russian is these days, George, but poshlost was the word, secondhand rubbish. Why are you dealing with this stuff? Later they said they're sorry they didn't listen to me, and I'm sorry I didn't listen to them because there were some people working on gauge theories. Not in the group I was immediately in.
The birth of this theory was actually very difficult, as we see. So let's go on to the next talk. We're going to have three. The next three talks will be on the experiments. And before these talks start, I want to make a few remarks. First of all, the discovery of quarks was a group effort. There were a number of people who participated, and they all played essential roles. And I must say, the graduate students were extremely effective, and they made very, very crucial contributions to actually this discovery. So I really want to salute the young people who actually did so much good work in this effort. So our next speaker is Marty Breitenbach. Marty got his senior thesis and PhD on the deep inelastic work. As an undergraduate, he worked very hard at developing detectors, and as a graduate student, he worked very hard in actually doing the experiment and the analysis. Marty, after he left MIT with a PhD, he went on to an extremely distinguished career at SLAC. At SLAC, he made important contributions to the discovery of the J-psi and actually spearheaded the discovery of the psi prime. So Marty has those under his belt. He also was the co-leader of the SLD collaboration, which produced extremely interesting work in the electroweak sector. So I'd like to welcome Marty. Also, I should say, he won the Panofsky Prize in 2000. So I'd like to welcome Marty to the podium to give his talk.
Thank you, Jerry. So I want to talk today, I want to describe the very early days at SLAC from the viewpoint of a young experimentalist. And the physics was waiting for us, as you've heard. The accelerator and spectrometers were ideal for the physics we wanted to do, and the leadership was great. In addition, the agencies and the laboratories had not yet invented reviews, and so it was indeed a golden age. So I want to dedicate this talk to Dick Taylor, who was the leader of the SLAC Group A that collaborated with Jerry Friedman and Henry Kendall. And Henry was the co-leader of this program. They're both shown here in perhaps their natural habitat. And at SLAC, with the recent death of Burton Richter, all of the founding giants of the laboratory are gone. It's very much a different place. So I was a bicoastal MIT grad student, beginning in becoming bicoastal in '66, as Jerry said. And travel was very simple. I had an MIT travel card. I just use it. As far as I knew, there was no accounting. So Jerry, I hope I don't get you into trouble at this stage. And for the young people, this is what we flew on. There was a company called Pan American. It was real, it was very nice. And those things on the wings are called propellers, and they made the plane go slowly across the country. So the Quark background, this has been started already very much today, that roughly in '64, Murray and George started this. It was a means of generating the eightfold way. It had spin-half and fractional charges, worked for hadrons with 3 valence, quarks for baryons, quark anti-quark pairs for mesons. There were many searches for the free quarks. None were found. However, from Murray, we know that mesons and baryons are mostly, if not entirely, made up out of one another. The probability that a meson consists of a real quark pair rather than 2 mesons or a baryon and anti-baryon must be quite small. From BJ, despite what Chris has said, additional data is necessary and welcome in order to destroy the picture of elementary constituents. So indeed, there was lots of confusion. So the real purpose, as we said in the proposal of the inelastic program, was to study electric production of resonances as a function of momentum transfer. I'm pretty sure that the words deep inelastic does not appear in this proposal. And even it was considered to be boring enough that our Caltech contingent, Charlie Peck and Jerry Pine, and actually Barry Barish was there, decided not to participate in further studies. So this is also the beginnings of a relatively large and effective collaboration among particle physicists. It's new. This is no longer a group of 3. It was, wow, it was 10 people or so, leading to the ability to directly build large and complex experiments. The spectrometers were a very big deal. Another aspect of this, which is important, and I'm glad to say it here, university faculty could not participate in these bi-coastal collaborations because of teaching responsibilities. And MIT initiated the concept of genuine teaching relief, not just postponement of the teaching, so that they could engage in this research. The other aspect that I remember very clearly is how international it was. Taylor's Group A invited many European visitors, particularly from Germany, beginning close relationships with SLAC that still persist today. So a little bit about the times. So this is, for those of you who don't know, this is SLAC. There's a highway that's there now, but it wasn't there then. But there was an overpass that was put in because Panofsky was worried about the disruption from pile driving for this overpass. But the timing was particularly tricky at that time because along the length of the LINAC, waveguides had to be installed from the top, and they were 10 meters long, and they had to be installed vertically, so if the overpass was there, the waveguides wouldn't fit. But all of this was worked out, and was just another aspect of Panofsky's foresight. At that time, the Homebrew Computer Club, most of you have heard about, was meeting in Panofsky Auditorium, and here are Steve Jobs and Steve Wozniak with what became the Apple I. All of the physics grad students were far too busy to spend any time with these guys who were just having fun. It was the summer of love in San Francisco, and that took a little bit of our time, and there were also the Vietnam War protests, which also took a little bit of our time. So this is End Station A. This is what went on. There's an incident beam. As Chris mentioned, there's indeed a target. The geometry is very simple. There is an 8-GeV spectrometer, a 20-GeV spectrometer that rotate about a common axis. Here, there's also a 1.6-GeV spectrometer that played only a fairly minor role in what we did, but it was there. The spectrometers specifically are used to measure the angles and the momentum of electrons by making sure that they are not pions. Okay, so this is an actual picture. It's probably worth pointing out that these are rails on which the spectrometers rotate. They can be driven remotely with a little bit of care. And they may still be among the larger pieces of experimental apparatus that can be moved macroscopically routinely. And that was done. So the beam is momentum analyzed coming in here. It goes into a hydrogen target. The earlier hydrogen targets was simple reservoir with cooling. That was okay for in the early days when the beams were small, but there was too much boiling and you couldn't tell what the target was with a bigger beam, and we got into a recirculating target, which was much more complex, but did the deed. And again, this is a view of the HF, and you can see that. So the spectrometer instrumentation and the electronics for both of these spectrometers were designed and built by MIT. This is a view of a momentum hodoscope, a precision machined aluminum array for holding scintillator and photomultipliers. These are the trigger counters, again, scintillator and photomultipliers. And here is the pi-e separator, which we now call an electromagnetic calorimeter. And this was designed long before anybody knew about the programs EGGS or GÉANT to make this a relatively straightforward Monte Carlo design problem. This is the end station A counting house. This is the SDS 9300 computer. It was a great computer for its time. It was about a 1/4 megaflop. And my phone, last time around, was about 500 megaflops. And this machine had 96 kilobytes of memory. The arrows have disappeared from this presentation, Chris? Okay. This is a teletype. This was what we would now call a human interface device, and it was more or less the only human interface device. This is one channel of an ADC. I mean, now, so that's these fit, I think, 2 across in the rack. One channel, to amuse you. These are called scalers. They're Nixie tube displays of counters. Such things are long gone. And this was the only video display. It was in high demand as the only display at SLAC at that time on which you could play Star Wars. And these are the so-called discriminator coincidence buffers that you would now do in a tiny pixel someplace. It was done with discrete transistors. The ICs were not yet on the scene. These things, by volume, were perhaps 2 liters a channel. And if we were designing something today, it would be about 10 to the minus 9 liters to get the same functionality with far better performance. Okay, it was a very serious beam. This is a view of probably a 500 kilowatt beam demolishing a copper block. Someone had to be careful with these things. And I want to go through the first experiments for a bit. The first experiments were E4A, which is elastic scattering of electrons on protons. These high Q-squared measurements were a wonderful lesson for me. At the highest Q-squared point, Q-squared of 25 GV over C squared, the expected rate, I think, was about 1 a day. And in the first day, I don't remember precisely, but we had roughly 10 events. And certainly I was beginning to get rather excited, and Panofsky comes in and says, stay calm, statistics are nasty. And indeed, after about 10 days of running, that particular point wound up low. So, okay. E4C was a comparison of electron and positron scattering on protons. This was done mostly by the Caltech group with me, because the rest of MIT and the rest of SLAC didn't think it was going to be fun, and it wasn't really very exciting. And then E4b was the deep inelastic scattering. It was the first data was taken at 6 degrees and 10 degrees. And as I've said, nothing really exciting was expected, but that was rather wrong. So I want to go through a typical problem that we had. So this is the same picture I showed you before, but it now emphasizes the beam after it's passed through the target, going out on its way to a beam dump. And this beam goes through a protection collimator to prevent the beam pipe from getting hit by whatever might come through. And there was significant backscatter from this collimator, and it was causing backgrounds in this detector. So we added some shielding here, lead bricks with a hole in them for the beam, of course, and it's stacked on a wooden table. And this is a view of it, lead bricks stacked on a wooden table. And the backspray from an 800 kilowatt beam can be significant. In fact, it melts lead. And when you melt lead, you ignite wood. The smoke alarm worked. The SLAC fire department came with their self-contained breathing apparatus because they didn't want to breathe radioactive smoke. But without the beam, there was only smoke, so it was no big deal. And we put a steel sheet under the lead bricks and resumed running in a few hours. There were no committees, there were no reports, there was no fuss. And I even wonder if Jerry even knew that this had happened. So, okay. So this is the elastic scattering summarized. This is the view online on that display I showed you. This is above, so you can see the peak and the radiative tail. And this is the comparison, and here's that last point coming in a little low. But there's nothing exciting about the elastic. So I think Chris has gone through this pretty much all we need to. So you indeed have the cross-section that we measured is the Mott cross-section and then the two structure functions. And these are the only things, these two structure functions for the proton and neutron are all the information that can be measured by scattering unpolarized electrons on an unpolarized target and detecting only the scattered electron. Radiative corrections were a technical challenge. What happens is that the simple process, which you see here, can also have final state radiation where an extra photon goes off, or it can have initial state radiation where a photon goes off. And in either case, it means that the energy of the photon is not what you thought it was. And this has to get fixed. I looked around deep, deep, deep in my files, and I found this note from Jerry on radiative straggling. I don't want to go through this at all, but it was just give you an idea of what was involved before there was Jean to do all of the hard work for you. So here is a view of the resonance region as measured, and then it's getting off into the deep inelastic. This is after this is the same spectrum with the radiative corrections, and this is the ratio of before to after. So once you get into the deep inelastic, the radiative corrections are quite important. So the data. We did a lot of calibrations for the spectrometer magnets with a floating wire with a current through it, and where was the elastic peak, provided a nice cross-check. By modern standards, the analysis was kind of simple. It was a counting experiment. You decided whether for each event, whether it was an electron, whether it was in the acceptance of the spectrometer, and you put it in the bucket. As I said, elastic scattering was interesting, but not dramatic. And for the inelastic, it was really pretty weird. For the deep inelastic, there was a very weak Q-scatter dependence. Here is the elastic scattering dropping like a rock. And here, the inelastic cross-sections barely drop. There was a memo from Dick Taylor in '68 saying the dependence of the deep inelastic scattering, missing mass W greater than 2 on Q squared is much weaker than the elastic dependence. This scattering, therefore, becomes a dominant feature of the data, even for moderate Q squared. So BJ, certainly in '69, using current algebra, argued that in the limit of large nu and Q squared, a scaling variable, 2m nu over Q squared, you could write W1 as some unique function of omega, and nu W2 as a second function of omega. And this is making an assumption about the ratio of the longitudinal to transverse cross sections. This is the data versus omega for W1. Here's nu W2. And indeed, it all seems to fit on the same curve. The dynamics of this scaling, as Chris has said, took a long, long time to sink in, although the word quark appeared in the first deep inelastic paper. So again, this is a cleanup of graphs plotted by hand by Henry Kendall and BJ in the counting house. And they were doing this in real time. We all knew about scattering. This is whether the ratio of longitudinal to transverse is 0 and the other way around. You can see the difference is probably best somewhere in the middle. And we all were talking about scaling. It was a very, it was the way that we were thinking about this, but what did it mean? Here is a better plot of nu W2 versus Q squared for fixed omega, and it's totally flat. And this is data from both the 20GeV spectrometer and the 8GeV spectrometer. So partons. You've seen this before. Feynman came, and when he came back the next morning, he showed us this picture and explained the trivial kinematics, so that scaling just fell out of this picture with partons. And compared to the... BJ has said all about scaling, okay, but to connect the scaling with partons for us, for me, was Feynman coming and telling us this. And here's Dick, I think at a second trip a few months later at SLAC, describing how all this worked. So after a lot of work in the dark nights at SLAC, here were the first papers that we're celebrating today. This is 1969 in October. We're just right there. And there are two papers on the high energy inelastic EP scattering at 6 and 10 degrees and observed behavior of highly inelastic electron-proton scattering. So eventually, the notion that from PEEP, theoretical speculations are focused on the possibility that these data might give evidence on the behavior of point-like structures in the nucleon was accepted. And these guys won the Nobel Prize. As Jerry said, it was a group effort, and they took the group to Stockholm. And this is a picture of the gang in the hotel in Stockholm before the ceremony. So in the early 70s, nucleons have a point-like constituent consistent with quark charge assignments and spin half. QCD explain the absence of free quarks. Asymptotic freedom explains scaling but needs deviations from scaling, which indeed show up. Bootstrap, nuclear democracy, VMD, diffraction models are all fading away. Color fix the Pauli principle problems. QCD gluons carry half the nucleon momentum, the rest by the quarks. So it was in good shape. So in the 60s, early 70s, these SLAC MIT deep inelastic experiments provided the experimental evidence, first for partons, and then their identification as quarks. And in the next two talks, Ari and Michael will describe the experimental basis for that justification. Thank you.
Thank you, Marty, for bringing back such wonderful memories. Those were great times, and it was a wonderful description of them. I just want to make one point that Marty mentioned. When we first did the elastic scattering, we essentially got the extension of the dipole form factor, which wasn't very interesting. And we decided that we had to do something else. And we just decided that possibly looking at inelastic scattering, the inclusive, might be informative. When we brought this to the program committee, they were grossly uninterested in having time for such an experiment. I was told it was a waste of time, et cetera, et cetera. And so we had to promise that we would measure the form factors of the various resonances, which we did. These form factors fell more or less like the proton form factor. It really wasn't very interesting, and we never published it. But in the process, as Marty said, we noticed that the deep and elastic cross-section didn't fall very rapidly with Q squared, as some people expected. And when we showed the program committee these results, then we got as much time as we wanted, and that's when the program proceeded. So now we have time for about 2 questions. Do we have any questions here? I think back there. Okay, I can't see.
You're not allowed. You have to use the mic.
So you made a point of emphasizing the issues of designing in an era before easy simulation packages. It sounds like that led to doing some more things by trial and error. Is that true, or did you do a lot of calculations in designing the spectrometers ahead of time, or was it more like things with the backscatter, where you try it, you see that you have a background, and you have to deal with it?
I think the answer is both. For things like designing the spectrometer, you had to work very hard and make sure you get it right. It would be far too expensive to make any modifications like that. Backscatter, put up some more lead bricks, sure. I mean, we did things like line the interior of the concrete shielding with lead bricks also to help it. It was easier to kill that stuff at the source. So I don't think it was impossible to do these kinds of calculations in a way that was adequate for the purpose. But boy, I could just dream of having Géant 4 available.
Any other questions here? Well, in which case, let's thank our speakers for very...
There was one question here.
One over here? Okay,
Sorry.
Yep.
Just to add on what Marty said, we worried very hard in the design stages and used some, shall we say, rather unique things. There was, Marty didn't mention it, and it didn't affect this experiment, affected the photo production experiments. But we had a beam dump buried down in the ground in bending magnets to take the residual electrons after they went through a radiator upstream of the end station for those who wanted to do photo production experiments. And we got something like 25 or 30 15-inch gun barrels from the US Navy that had been taken down when ships were decommissioned, filled them full of bullet stock, and put them in a position where that steel would shield background from the photo production dump. So there was a large amount of effort to try and use our wisdom to think about as much as we could in advance. We didn't do it all, and Marty showed you the pictures of the lead wall that turned up, give us the fire. But people pushed very hard to try to understand what could happen based on past experience.
I guess now we should end the session. And let's thank the speakers for their very, very interesting talks this afternoon. And the next session will begin in 20 minutes. Thank you very much.